Hello, my name is Thiago Lima. I'm a medical physicist responsible for the radiology and nuclear medicine department in the Luzern Hospital in Switzerland. First, I would like to thank the organizers for the opportunity to present my work. Today, I'm going to talk about the work done with colleagues from the Hospital A.I.L, also in Switzerland. The content of my presentation is that I'll first cover a little bit of the introduction on the subject and the problem we want to tackle. I will then describe the platform and model used and how we validated. Lastly, I'll present my results and conclusions. Özden et al. Described the challenges in characterizing image quality in CT. The so-called objective metrics like signal-to-noise ratio, noise power spectrum, MTF, which once were used, have become questionable with the introduction of iterative reconstruction. On top of that, the translation of these results into observer impression is not always smooth. Other metrics based on visual assessment are understood to be more clinical relevant with better acceptance between the clinicians. The main challenge is that direct evaluation with the human scoring is time-consuming and prone to inter- and intra-observer variations. Lastly, we have mathematical model observers. The problem is that these always overperform the human counterpart, and they still require the introduction of noise to match the performance of the human. So what's the problem that we have is that we've developed our in-house phantom to score image quality ST based on low contrast lesions. We have three anthropomorphic phantoms, a head and two body phantoms. The individual characteristics are described in the table. All phantoms have inlays with the lesions of different sizes and contrast. For the body phantom, there are two inlays, one with the lesions made of contrast media material, which iodine, and the other made with PMMA, which is the same material as the phantom. The problem arises is because yearly we have 43 devices to evaluate and to characterize and to optimize for different clinical protocols, which can be very time consuming if we want to do these based on the human observations. So the aim of this work was to develop a platform for CT image quality evaluation based on machine learning created to replicate the visual assessment by human observer. This is an overview of the workflow. First, we extract the specific inlay, remembering that there is two for the body phantoms. And then we cut out the lesions, and then we feed this to our model. The first part, we use a detection algorithm based on the RANSAC. And this is to automatically extract the inlay from the input scan. Then, once we know the inlay, we cut out regions of interest, which is actually volume of interest because it's a 3-dimension. Whenever it's needed, we use a mirror padding. And also it's important to note that within the ROI, different lesions will be present. So the model was trained to disconsider the surrounding lesions and only score the visibility based on the center lesion. And once the ROIs are extracted, they are fed through our model. And how our model works is that our model predicts the probability of these lesions being visible for a given observer. The model consists in two parts, a convolutional neural network predicting a score S, and an observer transformation mapping the score S to the probability of this given observer to have seen this lesion. We defined 2 degrees of freedom for each observer, characterized by alpha and beta parameters, and beta can be interpreted as the detection threshold, and the alpha is the consistency. The simplicity of this model allows for interpretability and post-training fit to the new observers based on little training. And additionally, since the last convolution layer in the squeeze net already allows for a linear transformation of the score, we fix the alpha and beta parameters for the first observer to 1 and 0 to foster reproducibility of the obtained scores. And as I mentioned, as is written, we have got 3 observers or 3 readers to label all the data set. And this label is consistent in a binary choice, yes or no, for visibility for given lesion. And then we use dataset augmentation, flipping rotation, to make the model more general. And we also used bagging to decrease the prediction variance. And by that, I mean that we trained 5 independent models on different folds of the trained data and average the prediction of all models at the test date. The first part of the validation consisted in assessing the accuracy of the inlay detection component of the platform, and that is for all inlays and phantom combinations. The second part consisted in assessing the scoring accuracy of the model. Since we trained 5 different models on each different fold of the test of dataset, we could use a cross-validation for this step. Each individual model is evaluated on its validation set. We furthermore extract the learned parameters alpha and beta for individual observers, and all validation steps were performed on unseen labeled data. And the model performance was evaluated versus its human counterpart. Lastly, we evaluated the capability and performance of the model versus the synthetic data, which provides a control changes of relevant conditions, and against real data. On the inlay extraction part, we computed the correct extraction of the inlay position, and our algorithm was able to correctly extract 99.7% of the cases, and for the 0.3% of the cases where was incorrected extract the inlay, we had do a manual positioning of the inlay. The model was then evaluated based on the ability to accurately reproduce the choices made by different human observers. And the table on the right shows the accuracy obtained for given observer and also the fitted parameters for given observer. The second part of our evaluation was to characterize the model performance and define control conditions with the synthetic data. First, we looked at the impact of the lesion contrast in the visibility. As expected, with the increase of the contrast from the lesion, the visibility increases. And also, smaller lesions require a larger contrast, so the lesion can become visible by the model. Second, we look at the impact of the noise. We start at no noise and introduce the noise slowly. As expected, with the increase of the noise, the visibility is degraded. And as you would also expect, these will depend on the lesion contrast and also the lesion size. Larger lesions and higher contrast lesions will start to be affected by only at the higher noise levels. Last, look at the impact of the surrounding lesions. As you may recall, the placer ROI will not likely, but will call for different lesions, and the model is meant to concentrate only in the lesion in the center of the ROI. For this part, we increase the contrast starting at 0 of the lesions not in the center and evaluate the impact of the probability of visibility. As you can see, when the lesion was visible, which is represented by the orange curve, even with the increase of the contrast of the external lesions, there was no change in the visibility. And the same was observed if the lesion was initially not visible, which is defined by the blue line. Last, the part related to more clinical performance based on the real measurements. First, we look at the impact of the dose, and as expected, the visibility of different lesions by different sizes increases with the increase of the dose for a given protocol. And this was observed for both native and the contrast media inlay of the phantoms. Then we looked at a different reconstruction method, and as expected, the iterative reconstruction is more visible, which means that there is more likely to see the lesions at a given dose, and in relation to the filter back projection. Last, we look at the different kernel strengths, and we observe the impact of the lesion size and the dose on the visibility by different kernel strengths. And here we compared the visibility in terms of minimal visible contrast. And as expected, the stronger kernel tend to be used to improve convergence for smaller lesions. So in conclusion, machine learned techniques provide a reliable method for human prediction of detectability, Our platform handled all the required image processing and scoring based on human low contrast visibility. This indicator enables the evaluation of large dataset without the variability and time costs associated with human scoring, and these can provide a reliable and relatable metric for dose harmonization and image optimization. Thank you for listening.